a white paper to set the white balance, a homemade clapboard to synchronize video and audio. Let's do it again. That should be it. Hi, and welcome. I'm Michael Hansen, and I'm going to start something quite new today. As you can probably see, I'm not at my usual place. I'm actually at my parents' house. Because this is still summer vacation for me, for my children. But I thought that I wouldn't want to cheat you for, well, some content anyway. And this time this is going to be some brand new content. So this is not going to be a game. Obviously, I don't have my gaming computer here. Also, it is not going to be something that has anything to do with flat Earth whatsoever. It is going to be me telling you about science, just the way it should be. And in this session here, or course or whatever you want to call it, I'm going to give you what I would say is an introduction to astronomy. A basic introduction, albeit at high school level, but nevertheless an introduction to astronomy. So if you have attended high school, or you are attending high school at the moment, and you have some basic physics under your belt, you have some basic math under your belt, probably you should be able to do with higher level elementary school math. But nevertheless, if you have some ground basic level high school math, that is going to help you anyway. But I'm going to introduce the course as we go. And this video here is going to be called Introduction to Astronomy. And I know that's a bit of a misnomer because this course is an introduction to astronomy. But nevertheless, this is going to be an introduction to the course, and the entire course, or whatever you want to call it. It's not a real course because it's not a teaching session. You don't hand in assignments that I correct and then give you back to you. You're going to watch my videos, and then probably I will give you some assignments that you can, if you will, can email me, and then I might correct them. I can't promise you that I will have the time for it, but if I do have the time, I will correct them. But let's take that as we go. Right now, let's just start this course in the correct way. Alright, so as you can see, this course is called Introduction to Astronomy. I'm Michael Hansen, I just told you, and this is YouTube University. Sorry, I just couldn't help myself. And this is the 26th of July 2019. It should have been in English, but that doesn't matter. You can read it anyway. Also, yes, if you did notice on my on the video of my face, I am wearing a pair of headsets, and unfortunately my old Sennheiser HD208, I think they're called, headsets broke down. Something happened with them, so one channel seems to be gone, it sounds muffled and wrong and all the things. So I've borrowed another pair of headsets, and the general idea is that as I sit here and I talk to you into my microphone, I can hear my voice without latency or anything like that, in order to see if I clip or if it sounds correct or if there's too much background noise and all those things. Let's get started with this course. So the basic question that you would probably want to ask yourself right away is, what is astronomy actually? And from my perspective, I would say that astronomy can be sort of viewed in two different ways. Actually, it's four different ways, but two basic ways and then two underlying ways. So the first basic way is measurements, classifications, and mapping of stellar objects. That is also what you could say is some sort of classical astronomy. That is the astronomy that the old Greeks did, that Aristotle did, that Newton and Galileo and all those people, Monsieur, who made the Monsieur catalog, all those people made what we call classical astronomy, or just astronomy. The other part, or the other understanding of astronomy, is when you look at the more modern way of thinking of astronomy, which is the understanding and explaining the physical properties of stellar objects. So here we are more interested in trying to explain what the physical properties of these objects that we can see, these phenomena that we can see on the sky, what they actually are. This has also generally been named astrophysics. So classical astronomy is just astronomy, but modern astronomy is more astrophysics. Also, besides those sort of major distinctions in astronomy, we also have sort of the level that you work on. So this is not sort of the basic understanding of what astronomy is, but more the level that you can do astronomy. And of course, here we have professional astronomy, and we also have amateur astronomy. Now, of course, this is not a comprehensive explanation of what astronomy is, because in order to understand what astronomy is sort of in detail, you have to understand astronomy. So it sort of goes by the basic that astronomy is its content, but it's also a way of doing science. So it's both things. But let's go on. I'm going to tell you a little bit about the course in itself, and then we're going to talk about these two levels. I'm going to explain a little bit more about those, because I would suppose that there are sort of two kinds of people that would be watching something like this. There are, of course, high school students, maybe even college students also, that sort of wanted to brush up on the subjects that they have intended, the ideas, the concepts that they have been explained. But then I suppose there's also the general public that are just interested in astronomy in sort of a basic level, but perhaps is doing, as I am doing in my spare time, amateur astronomy. So that is why I'm going to take a look at what professional astronomers do, but also what amateur astronomers do or can do, if you will. But let's continue. So in this course is based on a high school entry-level astronomy course that I taught in the year 2018 to 2019. We have just exited what is called the school year in Denmark. I suppose it's the same in most other countries. But this course will be practically identical to the course that I taught at Roskilde High School, except that at Roskilde I taught it in Danish, of course, and here I'm going to try my best to teach it in English. So yeah. Nevertheless, I would recommend two books if you are attending this course. If you are a Danish student, a Danish high school student, or anything of the sort, I would recommend that you obtain the book called Det levende univers. And I can see that I have misspelled it. It is not Det levende universe. It is Det levende univers. But nevertheless, I suppose you can figure out how to search for it. If you were to translate this name, it would basically translate to the living universe. So it's not that far away. This book is written by Henrik and Helle Stup, and of course it is in Danish. I have also used content and ideas from the book The Universe. I think it's at its 11th or 13th or something like that edition right now. But if you look at some of the older editions, which from my perspective and for this course is just as fine, you can actually find them free. So you can download a PDF and then you can read some of the subjects that I will tell you about here. This book is, of course, in English. The first book, Det levende univers, it is, of course, at high school level because it is written for high school students, while Universe, it is written at college level. I will, however, argue that any reasonable, well taught high school student should be able to read universe and get most of it, most from it. So it's not, I wouldn't say it's a very hard book to read. The concepts are relatively simple and the math is very, very basic. I will also not add any complicated math to this course. And like I said, it's going to be based on Danish high school level. So the math is reasonable, okay. It should be reasonable for most people. Of course, if you have problems understanding some of these subjects, you are very welcome to write a comment down below or send me an email at the same mail that is connected to this profile here or this YouTube channel here. So yeah, you have ample opportunities for me to answer any questions that you might have. But of course, I do other things. I actually do other things than YouTube. So I can't guarantee you that I will answer right away, but I will do my best. So the content of these lectures will be, and I have simply translated the titles that I use at the high school to English. So first we're going to look at the night sky and the solar system. So this is basically the things that you can see if you just take yourself out on a dark evening, a dark night, and then just look around on the sky. Then we're going to look at the stars. So there are stars all over the place, stars all over. So we're going to look at what stars are, how they are made, how they die, and all those things. Then we're going to turn our attention to planetary systems and exoplanets. When we look at the solar system, of course, we're going to look at this solar system. But of course, our solar system has always existed to be sort of a template on how we would expect to see other solar systems out there, other planetary systems out there. But recently, and I would say recently is sort of within the last 10 years or something like that, the amount of exoplanets that we have been able to observe and catalog has exploded unreasonable much. And that is why exoplanets has become a very large subject and a very popular subject within the astrophysical and astronomical community, the scientific community. And so that is also why we're going to take quite a bit look at that. When I say planetary systems, we're going to get a more basic view. So like I said, our solar system is sort of the template on how we would expect planetary systems to look. But when we take a look at the planetary systems here, it is going to be a more basic understanding on how planetary systems would probably be formed and what would happen to them. And these ideas are, of course, both derived from when we look at how stars are formed, but also when we look at the exoplanets that we sort of observe out in the universe. And finally, we're going to talk about what I would call the near and the far universe. And I know that's a bit of a strange name because the solar system is definitely near. But when I say the near and far universe, it is the universe itself. So, and as you can see, this is a relatively big subject. So this is going to be the one that takes the most time and most effort for my part. But as you can see, we're going to look at the stellar clusters, so clusters of stars. Those are mostly observed within our own galaxy. Then we're going to take a look at galaxies themselves, how they are formed, how they look, their categorization, and all those things. Then we're going to take a look at galaxy clusters. So as you probably can see, sort of you'll probably get an idea that when you look at this, when we go from the solar system, we have a bunch of planets that are revolving around a star. Then within a galaxy, we have a lot of stars, probably with planets revolving around them. And then we have a lot of galaxies connected in what is called the local group. And then finally, there's some intermediates, but to keep this relatively short. And then finally, we have galaxies connected in galaxy clusters. And then finally, we're going to take a look at sort of the really, really big picture. And this is called cosmology. And cosmology is sort of almost an entire over subject, sort of a main topic in itself. So there's a lot of under subjects within cosmology. But cosmology is sort of the bigger understanding on how our universe is created, how it evolves, and ultimately, at some point, how it's all going to end. So these were the content of these lectures. Now let's take a look at the distinction between professional and amateur astronomy. And I'm going to keep this relatively simple and relatively short. Those of you who have watched my videos, I can hardly ever keep anything simple or short, but I will at least try my best. So let's take a look, shall we? So one of the things that you can definitely say about professional astronomy is that the budgets are reasonable much larger than they are for amateur astronomers. So that means that professional astronomers, they have access to bigger equipment, better equipment, and in overall, they have access to more equipment. But the other thing is that amateur astronomers usually don't share a telescope between more than 5 or 6 persons. With the exception, of course, of iTelescope, which is an online service with a bunch of telescopes which people can get access to and use. So, of course, you share a bunch of telescopes with way more people than just 5. But professional astronomers, they share these big telescopes, and there aren't that many of them. There are probably, I would say, something like 100 or 200 professional telescopes placed around on the world, and there are many more than 200 scientists, astronomers, and so on. And you have to remember and consider that for most telescopes there are direct access. So anyone that can write a really well put together proposal could actually end up getting access to one of these professional telescopes without even being the slightest near the scientific community. As far as I know it, this is definitely the case for this telescope here, as you can see on the screen, which is called the Nordic Optical Telescope. Now, I have been there myself as part of a course we did a couple of weeks. So we got full-time access to this telescope and could use it to obtain real professional data. So this telescope here is a relatively small professional telescope. It has a main mirror of 2.5 meters, and you might think to yourself, well, Michael, that's a pretty big mirror. And you are, of course, generally correct, especially if you compare it to a telescope like mine. My own telescope I have here, actually at my parents', has a main mirror of 20 centimeters. So, of course, 2.5 meters is much bigger than that. But you have to remember that most of these telescopes are bigger. There are 5-meter telescopes, there are 8-meter telescopes, and there are even 10-meter telescopes. And the extremely large telescope that the European Astronomical Society or Association is going to build, I think it's called ESA. No, it's ESO. That is going to have a main mirror, or it is a connected main mirror, so it's a bunch of smaller mirrors put together. But the main mirror size is going to be something around 30 meters. So it's a really big telescope. And you can even see on this image here that the telescope here is pretty big if you compare it to this person here, that are explaining the huge usage of these different instruments and all those things around here. So yeah, it's a pretty big telescope, but in the overall comparison of professional telescope, it is sort of medium-sized, perhaps even a small one, but something between medium-sized and small, I would say. There are smaller telescopes, but there are definitely also bigger ones. As you can see here, professional astronomers, we use computers and we use them a lot. So just to give you a quick reference, as far as I remember it, this is the control computer for the telescope itself. So as you can see, there's a list. I can almost see just by looking here that over here you have the names of the objects that are loaded into the system. Over here you have direct ascension and declination. You're going to learn what that is. And then we have the degrees and all sorts of things over here. So when you want to point the telescope at a given direction, you choose it here, and then you press a button, and the telescope will turn itself all the way around. Up here we have the guide star, so even a telescope like this, which is professional in all its way, a modern telescope, needs to be guided in order to stay centered on the same object. So that goes as well for amateur telescopes as well for professional telescopes. As I remember it, this is sort of a quick image of what we are observing. These two computers, actually it's one computer, but these two screens here are used to control the detector. So right here we are using something called fiber-fed shell spectroscopy, an instrument that they have, but we could also use the main sensor sitting on the back of the telescope, which is called alphos. Over here there's an image that are connected to the download server so that you can check your data and analyze them over here. And of course we have our own computers brought as well, and you also need cola. Definitely need cola when you're doing observations that late. So this is an image that we have taken, and if you have taken amateur astronomy images, you can look at this and say, well, that's okay, but I can match that. But you have to remember or realize that, for example, this object here is probably something like magnitude 20, 22, something like that. So it's really, really faint. And there are not many amateur astronomy telescopes that would be able to get an image of this object here. But yes, of course, professional telescopes and amateur telescopes do the exact same thing. They collect photons, and if you connect a camera, then you collect those photons into the camera, so they do the same thing. So of course there are things that amateur astronomers can see that professional astronomers can see. That's really not that difficult to understand, I hope. So one of the things that we can do as professional astronomers is to get spectroscopy. And this kind of spectroscopy that we have here, which is called slit spectroscopy, as far as I know it, it is just reasonable new for the amateur community. So within the last 5 years or something like that, but it has been a part of the professional community for many, many, many years. Now, what you see over here is what we call a 2D spectrum. So what that is, this is basically what the sensor sees. These lines out here, as you can see here, those are skylines. So this is light that are reflected by the atmosphere. One of these lines, and this is what I thought was really, really amazing. One or two of these lines was from the light from the cities that were pretty far away, and small cities on this island. So the light from those lamps was sent up, reflected on the atmosphere, and we could resolve them in the spectrograph. So what you usually do when you reduce, as it is called, a spectrum like this, is that you basically take what you see here and you select what you want as your main data, and then you put it out. This is called a 2D spectrum, and then you put it out on what is called a 1D spectrum, so one-dimensional spectrum. So basically what you see here, that is basically what you would see if you took this image here and then flipped it 2 times around 90 degrees. Then you would sort of, these peaks that you can see here are going into the screen as you see it here. All right. What we can do as professional astronomers that, as far as I know it, is not really available for amateur astronomers yet, is what is called a shell spectroscopy. So instead of taking slit spectroscopy, where we have this little slit that sort of allows light to come through, and then you have one single spectrum obtained from what is called a grism or a grading, depending on how you're doing it. Instead, you have sort of 2 different gradings put together so that you get a lot of lines of spectroscopy on your image. And that means that you can get high resolution spectroscopy over a very large area. Usually when you use grading or grism spectroscopy, you have to choose between high resolution or high range. So usually when you have a high resolution grism, you don't have that much range, and vice versa. If you have a high range, so going from a very low wavelength to a very high wavelength, you don't have that big of a resolution, so you don't get very fine details. But with a shell spectroscopy, you can get exactly that. And for the optical telescope, they use what is called fiber-fed Echelle spectroscopy. So phi here is fiber-fed, and ES is Echelle spectroscopy, and the instrument is called FIES or FIES. And of course, it is a high-res spectrum. And this exact spectrum here is a spectrum of a Wolf-Rayet star, WR136. You can look it up if you will. And so we use this primarily to try to determine the rotational speed of these Wolf-Rayet stars. So as we're going to talk about when we go into the subject about stars, these particular Wolf-Rayet stars are very big blue stars that have a lot of mass, and therefore they usually rotate very, very fast. So besides all of what you have seen for now has been optical astronomy. But of course we have other branches. So we have radio astronomy. There are two main advantages of doing radio astronomy. The first is, as you can see here, that we have a lot of radio telescopes that we can connect together using a technique called interferometry, which basically means that all the telescopes that you can see here can be connected, and then they will function as one large telescope all over. So the telescopes here, when they are connected together, they will represent a telescope of this size here. So hopefully you can imagine that that is a pretty big telescope. Also, radio astronomy has one other advantage. It is not as sensitive to cloud cover as optical. Of course, optical astronomy is very sensitive to cloud cover, because if there is cloud cover, you can't see squat. But radio astronomy is not that sensitive. If there is a very thick cloud cover, it can obscure even radio telescopes. But radio telescopes can function all night with a relatively light cloud cover and still get reasonable good data. This telescope here, this area here, is called the ASCAMA Large Millimeter Array, or in short, ALMA. And this is an example of the data that you can get from ALMA. So this star here, this image here, is an image of a star called TW Hydrae. It's a protoplanetary system. And what is very interesting about this, besides that you can see we have a really, really good resolution of this planetary system. Here you can see all these little lines here that are probably dust lines from forming planets. You can see in here in the middle, and they have sort of blown it out here, they have enlarged it. This circle here, this little circle here, is most likely representing what we would say is an Earth-like protoplanet. So this would be what we would expect to see if we looked at our own solar system at its very beginning. This is what you can get with radio astronomy. And this is another much older radio telescope, which is called Jodrell Bank in the United States. I recall. We also, of course, have this very, very famous person here, this very famous guy, the Hubble Space Telescope. And this telescope is famous for one or two reasons. The first is that it has existed since, I think it's 1999, and it had 2 service missions to it when it should be decommissioned, and it is still functioning, and it is still providing really, really good data. Now, I seem to recall that the coolant on the Hubble Space Telescope is about to run dry, and so at that point, the Hubble Space Telescope, will be decommissioned. But nevertheless, the Hubble Space Telescope has taken a lot of nice images, both pretty pictures and really, really good scientific data in both the optical and infrared. So that's the area where Hubble Space Telescope works. And now the advantage of setting out a telescope in space is that such a telescope doesn't have to deal with cloud cover or the atmosphere itself. So the atmosphere, because it is dynamic, because it is turbulent, is going to introduce noise in our images. It's going to make them blurrier. If you go out on a clear day, and then even a really nice clear day, but if you choose a day where there has been a lot of heat or changes in the weather and those sort of things, if you look at the stars just above you, they will possibly flicker a little bit. They might not even flicker. If you look at stars just above the horizon, you will see a lot of flicker. And that is because you are viewing that star through more air. And because you are viewing it through more air, you are also seeing more turbulence in that light. So that light is going to go straight through the atmosphere, and every time the atmosphere is moving up or down or sideways or whatever it's doing, it's going to bend or move, or whatever you want to call it, that light just a little bit, and that is going to make the light flicker. So that is why we want to put telescopes out in space, is because there is no atmosphere out there. At least it is so thin that we are not bothered with it. But modern ground telescopes have different techniques to sort of counteract the disturbance from the atmosphere, and I seem to recall that one telescope, I can't remember the name, might find out for you for the next lecture, actually managed to get images comparable in resolution to the Hubble Space Telescope. So that might be one of the reasons that there hasn't been a third or fourth, I can't remember, service mission to the Hubble Space Telescope. And they have, of course, also had another project, the James Webb Telescope, which is going to be launched somewhere within the next 50 years or something. They have delayed the launch for so many times that I can't even remember when it's supposed to go up now. But the next space telescope is going to be the James Webb Telescope, and it is going to function primarily in the infrared area, so no optical space telescopes for now. And that is obviously because we are using infrared to detect both protoplanets, but also exoplanets. I digress, let's go on. So one other very important area that astronomers use is the X-rays. Now, X-rays are used to detect hot gas in galaxies and clusters of galaxies, but since X-rays behave very differently from ordinary optical rays, they're going to be treated a bit different. So as you can see, on a normal telescope, let's go back to the Hubble Space Telescope, the main mirror is probably somewhere around here. Then you have a secondary mirror here, and then light comes in, hits the main mirror, is reflected back to the secondary mirror, and then reflected through a hole here in the middle, and then back to the instruments over here. With X-ray astronomy, that is not an option. If you put a mirror here, then the X-rays would just go straight through. So what we do then instead is that we take a lot of slightly bent mirrors and make them circular. You can see they're cut off here, so they go all the way around. And then we slightly bend the X-rays, just a tad. And then you have to concentrate the light on the sensors very far away. So this is why this telescope here, which is called the Chandra telescope, is very long compared to, for example, the Hubble Space Telescope. It is because we need that length in order to focus the X-rays on the sensor back here. But we have done that, we can do it, and now we can see X-rays as well. As you can see here, this is an image that I have not taken, but I have reduced it myself. And I have chosen 3 different wavelengths, 3 different energies of X-rays, and then sliced them together on top of each other. And as you can see here, stars and all those, everything that is radiating X-rays is going to be present on such an image. But more prominently, you can see the X-rays that are coming from this area here. And this center here, all of this is a cluster of galaxies, but this is the very center of those. You can probably see that there is a bright center here, and there's a little less bright area here, but they are both bright, and they sort of almost form sort of an ellipse, if you can imagine that. And this is the very cluster that I'm talking about. So here I have taken the X-rays from the Chandra telescope and then superimposed them on this optical image here of this very cluster. This is the cluster that I worked on in my master thesis, and the X-rays has been given the color red here, so you can see the center here. So the final instrument that I will mention here is the Swift satellite, which is recording gamma rays. So gamma rays is coming from gamma ray bursts. When we talk about stars, I will give you a little funny story about that. But I don't have any images from the Swift satellite in gamma rays, so I can't show you it. But as far as I know, what the Swift satellite is doing basically is first and foremost to detect these gamma rays, because they are sort of relatively fast blinks of gamma rays. And then what astronomers want to do is as quickly as possible to point the optical telescopes up at that point to sort of capture what is called the optical afterglow of such a gamma ray. So that is why the basic, but it also does basic science, get spectrums and all those things, energy diagrams of these gamma ray bursts. So the Planck is recording microwave, and again a little error in spelling. It is recording the cosmic microwave background radiation, which is used primarily to describe the early stages of our universe right after Big Bang happened. So yes, we also have the Planck satellite. We're going to talk more about the data from the Planck satellite and the cosmic microwave background radiation when we talk about cosmology. One other instrument that I want to mention, which is not really one that I have used that much or have gotten that much into in detail, is the LIGO instrument. So what it has done is that it has detected gravitational waves. So it's all the other instruments that I have mentioned so far has been within the electromagnetic spectrum, but this instrument here it is something completely different. So it has detected changes in the space-time itself. So that is really, really new, and it is a very interesting area. But like I said, I don't know that much about it, but I can mention a little bit about it. I think to recall that the name stands for Laser Interferometer Gravitational Wave Observatory, LIGO. Yeah, let's go on. Alright, so what you have seen so far is sort of my take on what professional astronomy encompasses, and of course this is a short introduction. There are many more details about what professional astronomy is, but now I'm going to give you a sort of a quick introduction to how I see amateur astronomy is. So let's continue with that, shall we? Alright. So what you can see here on this image is my own telescope. So this is a 20 centimeter Newton. I have my little camera here. I have a guide telescope here. So this telescope, its function is only to watch a given star that I can see and then make sure that my telescope is positioned at the correct star, so that the main telescope is positioned on the object that I want to record using my camera here. This is the camera here, this little cylinder here, and this circle or disc or whatever you want to call it, it is actually a filter wheel. So it holds 5 filters, I think, or 4 filters, where one is a black filter I use for dark images. I'm not going to talk much about that. If you want to learn more about how to do amateur astronomy, I might make a video series about that, the basic concepts of that. But this these courses here, or this course, is going to be about astronomy in general. But this is just going to show you what you can do with amateur telescopes. So this is a 20 centimeter Newton, like I said, or 8 inches, if you want to know. This is a relatively solid Skywatch EQ6 Pro, which is computer controlled. As you can see here, this is the computer that I use. Actually, the computer that I use is positioned out here in the garage. This is my parents' garage. But this is the computer that I am actually recording on right now. And the difference is that I use TeamViewer to connect to this computer out here. And then I can sit in the warmth of my parents' house and control the telescope, which computer is placed out here in the cold garage. So this is 2 images that I have taken with my telescope. They are a little bluish in it. Probably because there was a bit of cloud cover or something like that at the time I took them. It can also be that I haven't taken away the background that well. There are many things going on here, but these are some of the images that you would be able to obtain with a telescope and a camera like mine. I haven't used filters on any of those, so they are completely filter free. These are images that I have taken from the iTelescope series of telescopes. So this is one telescope, and this is going to show you what you can do with filters. So this is I think it's an oxygen 3 filter, which is set to be taken in the green area of light. This is an hydrogen alpha filter, which is said to be done in the red area of light. And then you have a blue color as well, which is sulfur 2. And when you combine those, you get a color image. What you can also do with such an image in its very basic essence is that you can say the red areas here in the image are very concentrated in hydrogen. The green areas here are relatively concentrated in oxygen, and the blue areas that might be around here has a very high concentration or relatively high concentration on sulfur. You can't do sort of exact measurements. You can get more relative measurements. So you can say by looking at this image that this planetary nebula here probably contains more hydrogen and more oxygen than it does sulfur. But like I said, it's only relative that you can say that. So now we have gone through what I see as sort of the most basic ideas in amateur astronomy. Let's take a look at now what professional astronomers would do with the data that they get. So one of the things that astronomers is very interested in doing right now is trying to figure out what the physical properties of the objects that we see on the sky, what those are. And this is sometimes, or perhaps most of the times, referred to as astrophysics. So let's take a look. So the first thing that an astronomer would do is to get some data. Now this particular data here is what I used for my master thesis. As you can see here, these elongated lines here, and they are all over the place actually. Those are gravitational lensed images. So when I make a model of such a galaxy cluster here, I use the position of these images here to determine the physical properties of this cluster here. You could do the exact opposite. You could use the physical properties of the cluster here to derive what the physical properties of these galaxies, these lens galaxies here would be. You can even reverse engineer the images that you have here in order to get a more reasonable representation of what those galaxies would look like. What we then do is that we construct a model. So the model that I have used for my master thesis is what is called an parameterized model or parameterized code, which means that you feed the model, you feed the code with a bunch of parameters, and then you try to fit some of those parameter values to the data that you have in order to get the best model possible. You can see it here. We have what is called a potential. It uses a specific profile. I think this is called the dpi profile. Then you have some parameter values, the center of the profile, the ellipticity, the angular position, the core radius, the cut radius, and so on, so on, so on. And then you try to optimize the cut radius and the velocity dispersion in this model. And also you have another set of parameter values here where we also have an optimization. So these parameter values that you see here are those, you can see that they are sort of going repeated here and here. Here you have the initial value, and then you have sort of the range that you want to reduce within. And this is how such a model would function. For this particular model here, you need to give it a bunch of galaxies. We have those over here with their magnitudes, but also you have to feed the model some data. In this case, the data is what we call images, gravitational lensed images, and their central position, how they are shaped, and their redshift. These out here, numbers out here, is the magnitude, but I have never used them in any connection when optimizing such a model, because you can get the values, the magnitudes from the model itself. So when you have all these placed and you are ready to go, then you run your model, and like I say, you wait a very long time. Particularly with this kind of program here, which is called Lens Tool. It's not because Lens Tool is a bad program. Really, it's a very good program, a very good code. I can highly recommend it for anyone who wants to play around with gravitational lensing. I even have an introductory video on how to use Lens Tool. So if you are interested in gravitational lensing and you want to run Lens Tool at its very basic level, then check out this video that I have. And when you have run your model, then you get some results. And those results you have to interpret. So what you can get, what I got from the results in this case, would be the mass of the cluster. So as you can see here, these are the 1 sigma or 68% confidence intervals. Those lines down here are the images themselves. And this is sort of the cumulative mass of the cluster. This line here, the solid line, is the total mass of the cluster. So as you can see, when we start out at 10 kiloparsecs and slowly move our way all the way out to 400 kiloparsecs, the mass is sort of summed together all the way out to the edge of 400 kiloparsecs, which I have arbitrarily chosen given that the images is right around, the outer images that I've used is right around that area. I would not say that you can use a model like this to sort of try to predict them or get the mass of the cluster very far out when you only have images that close. The results will be very uncertain, that is for sure. We can also get the mass density of the cluster. This is interesting if you want to determine in some ways whether this is most likely an galaxy cluster that is going to collide or perhaps even have collided, or it is a relaxed cluster, as we call it. So this is the mass density of the cluster. And again, these solid lines here, those are the total mass density of the cluster. We can also get some parameter values and some uncertainties on those parameter values. So the lines that you see here are the uncertainties on the parameter values themselves. And these gray lines that you can see going from light gray to black are the uncertainties in 1, 2, and 3 sigma. So that is 68%, 95%, and 99.1, I think it is, or 5.5% confidence interval for the entire model assembly for all those parameter values. So a plot like this you can use to try to see if you have what is called degenerative values, and you can do all sorts of interesting things with those. When you have a parameterized model, you can argue that the most interesting thing, of course, is the parameters themselves. In this case, not so much, but yet again, a little bit. And finally, I think it is, we can also get the mass distribution of the cluster. As you can see here, this is the mass distribution of the cluster halos and the galaxies themselves and all those things. I've not talked so much about in detail about how you interpret results from gravitational lensing, because this is not a course about gravitational lensing. It's an introductory course to astronomy. But there are different halos that you have in clusters. You have what is called the main halo of the cluster itself, and then all of those little galaxies that we have used, they have their own halos as well. What you see over here is the mass distribution of the halo, the cluster halo itself, and the red lines represent the distribution of X-rays, that is, to some extent, the distribution of the hot gas. And the idea is to try to see whether the hot gas is sort of aligned in the same way and in the same shape as the dark matter or the cluster halo as it is. And as you can see, this is basically this is the case. So this is also one other thing that you can use your gravitational lens data for. So this was the introductory video for this course here. I hope you have gotten a reasonable good idea about what this course is about, a basic idea of what astronomy is, and I hope it has given you an interest for learning more. And I'm going to post more videos so you can learn more about astronomy. So I hope to see you there. Of course, please remember, if you like this video, then give it a thumbs up. If you for some reason don't like this video, you can give it a thumbs down. And if you want to be notified whenever I release a new video about astronomy or anything, games or flat earth, if you're into that, then remember to subscribe to my channel and then click that little bell out there. Then you will get notifications whenever something new pops up from my channel. So stay tuned for another video about Introduction to Astronomy. See you then. Bye.